Okay, great. So hello and welcome to our our final Spring into STEM taster lecture. If you'd like to I can hand it over to you to introduce yourself.
Okay, yeah, thank you very much. Hello, everyone. My name is Dr. Yuanchang Liu, and I'm from the Department of Mechanical Engineering at UCL. The lecturer within the department and working on the research, focusing on the robotics, AI, etc. So today I'm going to give this lecture focusing on the marine autonomy, which is that I'm going to talk you through how we can apply the robotics technologies into maritime industries. And specifically, I'm going to talk you through how we enable the marine vehicles to be able to see the environment and do some planning during the sessions, and also how these marine vessels can control itself when they are operating in ocean. So first of all, I would like to, I'm not sure whether this lecture has been given by other academics from UCL mechanical engineering, but first of all, I would like to give a very, very brief introduction to my department. So my department is UCL Mechanical Engineering, which is one of the big departments sitting in the Faculty of Engineering Sciences. UCL is actually consisting of different major faculties, focusing on the major research activities. And the department is actually one of the first department in the UK, which encouraged the students to have the engineering-based higher educations. And we currently we are having 42 academics within the department with a very broad variety of research activities within the department. For example, we currently have 4 different research groups focusing on biomaterials, energy, and then the materials, and also the marine research. And I'm currently sitting in the marine research groups. And then I have my own research group within the department. Currently, I have several PhD students working with me, and also some MSc students each year where they do some individual project with me. All of these research projects are actually being around my general research interest, which is robotics, AI, and control. And in order to sort of enable the research activities, we need to sort of secure some external fundings from different resources to help us buy the research equipment, recruit research associates, etc. So currently, we're having some research support from European, from EU, from UK, and also from some other international funding agencies. Actually, in order to undertake the research, high quality research, we need to do the research in collaboration. And I'm currently working with working in collaboration with some universities within the UK, for example, University of Plymouth, Cardiff universities, and also some other universities from the States, such as Stevens Institute of Technology. So first of all, I would like to briefly tell you what is the general picture of my research activities. I would like to summarize my research activities as we actually focus on the theoretical designs, which will innovate robotic platforms and ultimately will enrich the practical applications. What it means here is that we firstly will design the different structure of the robotics, and then we'll look into different kinds of the softwares that can control the different robots. And then we'll look specifically how we can apply these different robotic platforms to different application areas. For example, we've been working on, this is probably you can recognize from this picture already. We are working on the UAV, unmanned aerial vehicles, or drone, and we apply we make the drone fly autonomously, and then we look at how we can apply these drone platforms into some applications, such as how we can use the drone to monitor the growth of the farm, or how we can use the drone to help the farmers to pick up the fruits or some other things. And similarly, this is the another type of the robotic platform called the ground vehicles. So we build up this platform, which is similarly to the you can call it self-driving cars or something like that. It has 4 wheels and also has some other sensors to help it recognize the environment. But anyway, once we build up this platform, then we think how we can apply these platforms into the specific application areas. And in this case here, we try to apply these platforms to support the space explorations by working with some other colleagues from other universities. And finally, this is the you can possibly recognize as well from this picture. This is one of the unmanned vessel that this is not the platform that built by us, but is a platform built by one of our collaborators in States. It's called the 1V Unmanned Surface Vessel, which is the one of the most commonly used commercial vessels, unmanned vessels in the world. And we try to then apply these platforms into some applications such as ocean discovery. So in today's talk, I'm going to specifically focus on the marine vessels, which is showing this picture here. So before we move on, possibly we need to understand what is actually the unmanned surface vessels. So the definition of the unmanned surface vessels are quite easy to be understood. It is actually the boat, but it can operate on the surface of the ocean without any human interventions. And according to the regulations, we can divide the unmanned vessels or USVs into different types. We have the ultralight vessel, which has the length less than 7 meters. And also we have the light class of unmanned vessels, which has the length between 7 meters to 13 meters, etc. And also we can group the different USVs based upon the operating speed. Normally, the operating speed of the vessel is about 5 knots, and sometimes if we have the high speed USVs, then the speed can be as high as 14 knots. And then after we understand what the USVs are, then we can give out some definition about the degree of autonomy. So because ultimately what we want to do here is to make sure that the boat can sort of navigate on the ocean without just purely by itself. But currently the technology are not ready yet to ensure the full autonomy, which is the fourth degree here, called full autonomous ship. The definition of the full autonomy is actually, which is written here, that the operating system of the ship is able to make the decisions and determine the actions by itself, which means that all the decisions and all the control actions are actually happening on the boat without any human intervention. However, as mentioned, the technologies are not ready yet. So most likely that all of the USVs currently being used actually belong to the degree of autonomy from 1 to 3. The degree one of the first degree of the autonomy is actually the ship with automated processes and decision support. This is actually happening almost on every single ship already. And then the second level is the remotely controlled ship with with the human operators on board. And for example, some automated maneuvers can actually being used during the when the ship is on voyage. And the third degree is actually the remotely controlled ship without any human on board. And in this category, then the ship is actually controlled and operated from another location, for example, a base station on shore. So as we probably know, the unmanned ships are quite promising, and one of the major things that we actually need to be we need to do is actually how we can test and validate the capabilities of different unmanned vessels, and this consequently requires to build up some testing sites and facilities. And actually, the UK has been pioneering in this area by building up a lot of different testing sites. And you can possibly see from this map here that we have a lot of testing sites in the South England and also the southwest part of the UK, and also we have some test sites in Scotland and further north. So that's pretty much some very brief background introduction to the USVs. Then now I'd like to talk you through some major applications by using the USVs. As you can probably imagine, one of the most commonly used application areas for USVs is actually the military applications. We use the USVs for the coastal patrol, and also sometimes we use the USVs as the seaborne targets, and also we can use the USVs for minesweeping operations. In here, I'm showing you three pictures. Actually tell you to actually understand what the USV looks like. For example, in this picture here is one of the flagship USVs developed by the UK, actually by the company called the L3 Harris. It's one of the major USV companies in the UK, and it has been used by the Royal Navy actually for some operations. And this is another picture, another vessel developed as the Maritime Autonomy Surface Tested Bed. And actually you can see this the testing operation happening on Thames River. And apart from the military applications, we also use the USVs for the civilian applications for sure. We can use the USVs to support the ocean research, and we can use them for the environmental and climate monitoring missions. And most importantly, we can use the USVs together with some underwater vehicles to help to map the seafloor. For example, this picture here is actually how the underwater vehicle has been employed to map the seabed areas to help us understand more about the ocean. We tend to sort of deploy the USVs in collaboration with other types of the unmanned vessels, unmanned vehicle platforms. For example, in this picture here, one of the vision in the future is actually to use the unmanned vessel, which is this one, in collaboration with the underwater vehicles, some gliders, and also the drones, and most importantly, we can include the satellite communication together here to enable a full coverage communication. This picture here is actually another very famous USV platform developed in the UK. It is called the Seaworker 8 USV. One of the main features of this platform is that it has a long endurance capability, which means that it can operate. It can be operating on the ocean autonomously and for a 7-day ocean continuously. So without any return to the port, you can just continuously operating on the ocean for 7 days. Another I would say very famous project going on within the UK is actually the project called the Mayflower Autonomous Ship. It is an autonomous research vessel planned to cross the Atlantic Ocean without human crew or assistance. One of the main features of this, in this picture, this is the how the Mayflower autonomous ship looks like. So one of the main features of this autonomous ship is that it has a very high level of it has integrated a very high level of AI elements into the boat to help it sort of to support a fully autonomous operations. And the starting point of this journey is from the Plymouth in the UK and navigates through the Atlantic Ocean and eventually land in Plymouth, which is not the Plymouth in the UK, but the Plymouth in the United States. The cost of this project is around $1.3 million US, and is owned by a non-profit maritime research organizations called ProMare in partnership with the major computer tech company IBM. And one of the missions along the voyage is actually the ship will sample the water for pollutants and study the marine life during its operations. So here is a video that I would like to share with you to let you know more about this project here.
The ocean floor is littered with our engineering failures and mistakes. You need to respect the power of what happens out there.
There's still things to be discovered. If we have a zero risk philosophy, we are doomed.
When we first conceived this idea, I wasn't sure it was going to be possible. We were talking about an intelligent vehicle out in the middle of the Atlantic Ocean.
We built a ship, put autonomy into it, and now we're learning what that means.
You just maintain your constant speed. The pressure's certainly building as we're getting closer to the launch. There's a lot that we need to deliver.
Something going wrong.
What keeps me up at night is we break down somewhere in the middle of the Atlantic, and it's something so trivial.
Working on a boat like this, you kind of have to figure stuff out on your own.
Get some drama. No, we need to find out what happened. It wasn't responding. We'd lost comms. I just want to finish shaking her out and start a class. The crossing.
The crossing.
So when you say the crossing,
Atlantic.
that little bit.
Yeah.
Yeah, the blood.
When it pulls out of Plymouth, and I know it's not coming back for 6 months. When I see the rear end of it, the stern of it going around Rainhead, headed off west, that's going to be exciting.
IBM really likes projects that are really pushing the envelope to do really exciting and novel things.
What if we had hundreds of these vessels? This is going to transform ocean science.
Trying and failing doesn't bother me. It's if we don't do everything we can do to ensure success.
Okay, so you can probably see how challenging the task is, and in order to make sure that the boat is able to sail across the Atlantic, we need to make sure that a very high level technologies are integrated within the vessel. And one of the core technology actually associated here is what we call the autonomous navigation system. This is actually the structure that we have been keep on developing for several years. You don't need to sort of pay attention to the technical things inside this block, but what I want to try to get you to understand here is that the autonomous systems actually working as how like human perceive the environment and make the decisions. So our human use the eyes to actually see the environment, see the surrounding areas, and then, for example, when you're walking on the street, you can see where the other people are, and then based on this information, you can sort of do the planning within your mind and generate a trajectory which can help you sort of walk on the street without bumping into each other. So we, by following this idea, we come up with these navigation systems. The first thing is that we need to have different sensors to actually help the vessel to understand the surrounding area or the surrounding environment. And the sensors we use here include, for example, the GPS, which can tell where you are or where the boat is. And we have the compass, which can help the boat to understand which direction it is actually sailing. And also we have the IMU, called the inertial measurement unit, which is to record the velocity or the it should be the speed, the speed and also the angular velocity, etc. Of the boat. And also sometimes we use some other sensors, for instance, the automated information exchange systems, which is to record the other vessels, the other boats position and the velocities. And also we use the radar or the marine radar here to actually help us do the scanning of the environment and understand whether there's any obstacles or any other boats in vicinity. And then based upon all this information from these sensors, we can use the information into this planning block here. We can imagine this is just like the mind, our mind, and then our mind will sort of work out a trajectory. In this case, the waypoint, which will tell the boat what is the next point that the boat should be moving towards. And then the whole system is working in a loop, which means that all the information is taking in real time. The planning is going on in real time as well. And then there's some I would say technologies I would like to share with you by looking at how actually our boat is seeing the environment. Apart from the sensors I introduced in previous slides, sometimes we use other sensors. Most importantly, in this case, we can use the cameras. Yeah, the cameras will be more like our eyes when we are seeing the world. So we use the cameras to help the boat to see the environment. And in this case, we can see that the boat is able, the camera can pick up the environment quite vividly. And one of the major disadvantages, I would say, when we're using the cameras is that the camera is not able to deal with some environmental factors. For instance, in this case, we have a very strong fog on the water surface, and consequently, we could actually make a very good distinguish between where the water is and where the sky is. And another environmental factor is actually strong sunlight that we normally encountering on the water surface. For example, in this case, we are experiencing very strong sunlight, and then again, we can see a very strong reflections on the water surface, which will largely compromise the detection results of the camera. So in order to solve these problems in in one word, which is how we can develop some software or algorithms to help the boat to better process the the camera visions, camera informations, and consequently to help the boat understand the environment in a better way. And so my research group actually has developed some technologies here. You don't actually necessarily to understand what is happening here, but I can tell you the method we apply here is the you probably have heard about this before. Is the machine learning algorithms. So we let the algorithms or we let the computer to take in the raw information and then to to process the information by itself and to let the computer learn the environment itself, and consequently can produce some very amazing output, which will help the boat to recognize the environment. So here are some results. As you can possibly see, we taking the environment, we're taking the camera, the picture taken by the camera, and then the algorithm can output a very good results by distinguishing where the sky is, where the land is, and where the water is. So we do the separation of the environment and it's categorized different parts into different by its features. And here is a small video clip to show you how this process can be done in real time. So for example, this is an input image taken by the camera, and our algorithm is able to sort of divide this image input into a segmentation output, as I mentioned, by grouping by separating the image into sky, the land, and the water. So by doing this, we can sort of simplify the environment information and can let the boat understand where the water is and where the obstacles are, and consequently the boat is able to sort of to navigate in the ocean in a safe way. So this is all about the perception. And as I mentioned, once we understand what the environment looks like, the next step is actually to plan a trajectory or plan the route to help the boat to navigate in the ocean. And this is actually one of the I would say research topic, as we call it, as the path planning. So in other words, how we can plan the path in the environment. And in order to, when we are planning the trajectory or path, we need to take into several factors into consideration. For example, we want to make sure that the path or the trajectory has the shortest distance from the which can connect the start point to the end point. And secondly, we don't want the trajectory to collide with any obstacles, in order to ensure the safety. So for example, in this figure here, we assume that the white space is the collision-free space, which means there's no obstacles, and the black areas are all the obstacles. So we want to plan a trajectory. In this case, we can plan a trajectory, connecting the starting point to the end point without colliding with any obstacles, and also to ensure the distance is as short as possible. And then we can apply this path planning algorithms onto our USVs or the autonomous boats. And we've done some tests. For example, we can plan the trajectory for a group of vessels. In this case, we have 3 vessels, and we can do the trajectory planning for 3 of them simultaneously. And the planned trajectory also can avoid some moving obstacles en route. In this case, there's 3 moving obstacles, and the planned trajectory can avoid these obstacles in real time. And also we can plan the trajectory to follow the ocean currents. The reason why here is that we want to make sure that the energy consumption of the boat is as minimal as possible. So we want to plan the trajectory to follow the direction of the ocean current as much as possible in order to save the energy. So that's the planning part. And then another thing I would like to introduce you here is that, as you can probably know, the boat is amazing, but only to having a boat is quite challenging. And I'm not mentioning the to operating the boat in real oceans. So one of the things we are thinking of is that how we can sort of build up a simulated version of a, for example, a USV or autonomous boat, and also we can operate this vessel in a simulated environment and consequently test the capability of the vessels. And by following this idea, our group have developed some simulation environment. In this case, for example, this is real USV or boat that has been used, and then we convert this boat. We built a very real version of the boat in our simulation environment by taking into consideration, for example, the physics of the boat, the motion of the boat, and also the environment of the boat. And based upon this build up, this simulated platform, then we can develop some algorithm, for example, in this case, there's control algorithms to control, for example, in this case, to control the propellers and consequently to drive the boat in the simulation environment. We can also, for example, here, we can simulate the camera information or image information in a simulation environment. So, and then this is the, by using the simulation environment, we can then build up the control or the autonomous navigation systems, as I mentioned in my previous slides, in the simulation environment. And then we test it in a sort of very practical case. In this here, we want to deploy the USV to do some inspections of the offshore wind farms here. As you can see, the USV is traveling or is navigating through the offshore wind farms, and we can take in the real-time visual information, and we can record the trajectory of the boat, and as well as the real-time control signal of the boat. So that will help us a lot when we actually really want to develop something, when we want to do the inspection of the offshore wind farms. And the final part of my today's talk is actually, I would like to introduce you, is a competition organized by Society of Maritime Industries. This competition is called the Maritime Autonomy Challenge, or MAChallenge. It is open to all the universities within the UK by encouraging students to learn more about how to control a boat autonomously, and to help students understand more about what is the cutting edge technologies going on in this field. And so the aim of the challenge I've listed here, that first of all, the challenge wants to encourage students focus more on the autonomy, and then to get students thinking about how autonomy might address the problem of the plastic issues in the ocean. In other words, we want to deploy these unmanned vessels in the future to help us to sort of do the pollution collection missions in the ocean. And also we want the challenge encourage students to stretch the knowledge and promote the creative thinking. In other words, the challenge wants the students to use the learned knowledge from the university and apply this knowledge to help them have more critical thinking. And as and the challenge in inviting the students working as a group, and consequently that will help the students to develop some team working skills, but also some individual working skills. As I mentioned, the challenge is organized by the Society of Maritime Industries, which means that there are a lot of industry sponsors involved, and that will actually help the industry to see to know better about the students, and consequently maybe can recruit more young talents when the challenge is finished. And the specific mission within the challenge, we actually have 5 different challenges. The first one is to navigate around a track using a several waypoints. So this actually, as I mentioned, the challenge during the competition, the organizer will give you some waypoints already on a lake, and then they will require the boat to follow these waypoints, and consequently to track the trajectory. And the second challenge is actually to take in some traffic regulations, and which is to help the boat to avoid the other ships in the same area. The third challenge is actually very challenging, which is to understand how we can control the boat, or how we can let the boat control itself to dock into a berth and stop itself within 1 meter. This is very, very challenging because the berth is normally quite narrow, and the control of the boat is subjected to different degree of freedoms, which consequently constrain the motion of the vessel. The fourth challenge is to locate and map an area of the microplastic or pollution. This is actually we imagine that there are some pollution areas on the lake, and we want to sort of deploy this vessel on the lake and autonomously, and to collect this some pollutants from the water surface. And the final challenge is actually to search a specific box area and position all floating targets within it. So this is 5 different challenges, and we need to compete for different for all of these challenges, and will be scored based upon the performances. The way of this challenge, how it has been undertaken, is that because this challenge is actually the first challenge was last year, and which is during the COVID pandemic. So the way that we participated in the challenge is that the organizer sent out some platforms, some hardware platforms, and then we do the algorithm design on a simulation environment, and then we test the algorithms by using their hardware platforms, and in this in a simulator to see how the algorithm performs. And then once all the algorithms have been developed, then we send them back to the organizer, and they will help us test it on a real boat. So this is how they do it, how we do it. And this is a video clip showing you how the boat is actually performing on the competition day. This actually, I think, is the first challenge where the boat, which is this one, has to follow several waypoints. For example, this waypoint, there's another waypoint, and there's another waypoint. And then I will quickly show you how it is setting on the lake. So the boat is actually approaching the first waypoint. Once the boat has been within certain area of this waypoint, then it makes a turning into the next waypoint here. So as you can see, the boat is actually adjusting its direction towards, I would say, the second waypoint. As you can probably see, the boat now can recognize yourself, oh, possibly have already reached within the area of this waypoint, then it makes the decision to move towards the next waypoint, which is this one, and also by adjusting its speed as well as its heading direction. So the third waypoint has been reached, and then the next one, which is here. As you can possibly see, the boat is actually can nicely track each waypoint, and this proves that we finally won this competition. So we're the winner of this MAChallenge 2021, which is the first MAChallenge, and now the organizer is open for the second competition this year. So that's the end of my talk, today's talk. I hope you enjoyed it. And is there any questions or?
It looks like we have a few questions in the chat.
Okay, in the chat, let me have a look. Just say. So the first question is from Daniel. When you apply for a master's, do the admission care? I probably, because I'm not working with for the admission team. You probably need to speak to the admission team at UCL with regards to how this master recruitment is going. And the second is, what are the use cases for autonomous boat? Okay, as I mentioned, we have different application areas like military applications and civilian applications. Most likely, most commonly used applications are military based, but we are seeing more and more application towards civilian areas. And one of the most applied areas is actually as I mentioned, the seabed mapping, because we understand that we probably know every single part on the Earth of the land on the Earth, but only 7% of the ocean has been fully explored. So we want to apply these unmanned vessels to help us understand the oceans in a better way. And the next question is from Andrea. What do you think are the barriers to overcome to reach full automation? Okay, very good question. Let me take the autonomous vessels as an example, because different vessels or different vehicles is facing different challenges. For the marine vessels, the most challenging part, which prevents the full automation, is the variety of the environments. There's actually the big difference between, for example, the self-driving car and the autonomous boat, because when you drive the car on the street, the environment is actually quite stable. The road is not moving, and you actually have very enriched information that you can take into account. However, when you are sailing a boat on the oceans, then the ocean has very, very strong currents, which makes the ocean is moving up and down very significantly. That will make the control of the boat very, very challenging. And secondly, as I mentioned, the ocean is subject to different environment influences. For example, very, very strong sunlight, and that will compromise the image taken by the cameras, and also the fogs. If they're very strong fog, then basically you can see nothing on the oceans. So how we can improve the environment perception on the ocean, that is one of the most challenging things that we need to think of. I hope that answer your question. Then the next question is from Taro. As a researcher specializing in marine vehicles, what makes this field of engineering particularly interesting for you? Why did you choose to focus on marine vehicles and not land or area vehicles? Right, let me first answer your second part of the question. The reason why I'm focusing on the marine vehicles is because I'm sitting within marine research groups, and that will that basically has set up the general research direction for my research group. But as you can possibly see from my the slide in the first few slides, I would say the majority of my research activities are focused on marine vehicles, but also I'm very interested in the land vehicles and UAVs. Especially, one of my PhD is actually working on the aero vehicles to help us for the agriculture applications. And the first part of your question is, what makes this field of engineering particularly interesting for you? Yes, so I assume what you want to ask is what's the part associated with the marine vehicles is particularly interesting for me. This is because, as mentioned, because in general, if we want to make the vehicle, no matter this land vehicle or aerial vehicle or marine vehicle, to navigate autonomously, the general structure is the same, which is the autonomous navigation system, which includes the sensing, planning, and the control. And as I mentioned, the ocean environment is far more challenging than the other operating domains of, from other type of the vehicles, such as land and aerial vehicles. So if we're focusing on the marine vehicles and address these issues associated with the environment, then consequently that will help us a lot to understand better how we can design a better navigation systems, and subsequently we can sort of apply this improved autonomous navigation systems into, for example, the land vehicles and aerial vehicles, which will encourage the full automation of different types of the vehicles. I hope that answers your question. Any other questions? I think we're okay here.
Okay, great. So just to conclude, thank you so much, everyone, for coming. If you want to find out more about future events we have, check out UCL MAChallenge website. We have just write UCL Mechanical Engineering. You'll find us, and we have like an events page where you can find out more and maybe join us for future events. So from on behalf of everyone here, thank you so much for coming, and hopefully see you in the future.
Thank you very much. Thank you all.